Hi everyone, it's a pleasure to be presenting our work at the online version of eDBT. Today I'll be presenting progressive merges, merging batches of appends into progressive indexes. And this work was done by me and my supervisor Stefan Monegold at CWI in Amsterdam. So let's kick off this presentation with some quick motivation. In order to keep users' attention, interactive data analysis queries must be answered within a time threshold. These queries usually have filter and aggregation operators, and here we have one example of a classical scenario. On the top, we have a slide bar where the user selects the flights he wants to inspect, and the figure is automatically updated, taking the filter into consideration. It's easy to imagine that it can be quite frustrating if the figure takes too long to update. And in scenarios where the data is too big and you're constantly scanning it, it might happen. However, we can take the filter part of the query into our advantage. By smartly skipping data that does not fit it, we can drastically improve performance and keep our users happy. One way of performing data skipping is by using indexes, and progressive indexes are the state-of-the-art indexes for interactive data analysis. The technique creates incremental indexes. In other words, indexes are created during query execution and are heavily inspired by adaptive indexing. Like adaptive indexing, no idle time is necessary to create indexes, and they can be created without prior workload knowledge, since they are created while data is being accessed and use this access as a hint of what to index. Progressive indexes differ from adaptive indexes since they guarantee full index convergence. In other words, that after executing a certain amount of queries, the index will have the same format as a full index, and they have a robust query execution, where the per query cost doesn't change much up until full index convergence. One problem of progressive indexes is that we can only create indexes over static data. If we go back to our flight example, we can imagine that flight information can be updated daily and maybe hourly, since flights happen every day. Well, at least this was the case. Maybe nowadays it changed a bit. But prior to this work, there was no defined way of updating progressive indexes with new information. So before explaining the progressive merges techniques, I'll just go through some basic definition and a quick example of progressive indexes. The basic idea of progressive indexing is to make incremental index creation even more fine-grained and completely tunable to a user preference. It introduces an indexing budget delta that represents a fraction of the data, and that every query, a delta fraction of the data is indexed, up to the point that we have a full index. Here we have one example of progressive indexing using quicksorts. Notice that our delta is 0.5, which means that in every query we run half a quicksort iteration. We start off with a completely unordered column and a query filtering out elements higher than 10 and lower than 14. We initiate progressive indexing with a pivot of 10. When scanning the first half of the column, we copy the elements to our progressive indexing structure and position them in either the bottom or top part of the column, depending on how they compare with the pivots. For example, 13 is higher than 10, so it goes to the bottom. 16 also goes to the bottom. 4 is lower than 10, so it goes to the top. While doing so, we're also collecting the elements that fit our query, like 13 and 12. For the remaining half of the column, we just scan the elements to see which ones fit our query. After this, we create a node in a binary search tree holding the information about the pivots, where it starts and where it ends. For the second query, now requesting all elements below 4, we can already take advantage of our progressive index. We just need to scan the top part of our progressive index, and we continue the same process as the prior query on the remaining half of the column. At the end, we update our binary tree, and this process continues until we reach a fully sorted array. Now let's talk about progressive merges. Progressive merges, they follow the same progressive indexing philosophy by only merging a delta fraction of the data per query. It starts by progressively sorting chunks independently, then it merges them into one fully sorted chunk, and finally merge it to the progressive index. This technique incurs a low per query penalty, resulting in a robust per query cost, and it's actually up to 2.5 times faster than the related work. Here I give you an example of how progressive merges work in a high level. We start off with a progressive index column in some refined states, and our append batches are completely unrefined. In the following queries, we continue the refinement of our progressive index while also independently refining all three append chunks. And when a new batch of appends is inserted, we create a new unrefined append chunk to it. The more queries are executed, we will end up with a completely sorted progressive indexing and completely sorted append chunks. When we reach that point, we start to progressive merge all append chunks into one append. When we reach one append chunk, we merge it to our progressive index. Now let's see a more detailed example of how progressive merges work under the hood. In this scenario, we have two append chunks. They are completely unordered, and we set our delta equal to 0.5. On the first query, a progressive quicksort iteration is initiated on each chunk, and they are executed independently. You can see that the first chunk even has a different pivot than the second one, and that both index half of each chunk. On the second query, both progressive quicksort iterations are finished and the chunks are fully pivoted. The progressive quicksort runs up to the point that both chunks are sorted. When the chunks are sorted, we can now start the merge phase, where we actually merge both chunks into one. Again, since our delta here is set as 0.5, we only generate half the merged column in each query. We store pointers or where we are in each chunk, and we go down depending on how they compare with the lowest elements in the other chunk. For example, the top chunk's first element is 0 and the bottom is 2, so we copy the 0 to our new merge chunk and move the pointer of the first chunk down. We now compare 1 from the first chunk and 2 from the second chunk, and so on and so forth. So repeat this process until our new merge chunk is half full. On the next query, we can finish off the merge and delete the old chunks. Note that this merge strategy would be executed for all append chunks and eventually between the append chunk and the progressive index. Here we depict one of the experiments from our paper that compares progressive index with related work. Due to time constraints, I'm not really going to go into the details of why this is really happening and what the related work is. So I'm just going to point out some key differences here. The data size we use is 10 to the power of 8. Our query selectivity is 1% of the final data size. So the initial queries actually have a much higher selectivity than this. The batch size of the updates is 10 to the power of 4. And the updates are executed at every 100 queries, and they only start after the first 1,000 queries were already executed. The first thing we can notice is that in the related work algorithms, we have these big spikes upwards in the beginning of the updates, and that's due to high cost index resizes, while in progressive indexing, we don't really have this cost in progressive merges. So progressive merges are actually capable of smearing out this cost throughout the entire workload. The second thing we can notice is this, the related work has a lot more performance spikes upwards through the workload, while progressive merges don't. And the reason for that is because progressive merges actually keep a very fine-grained control of the time spent on merging each query. And the last thing we can notice is that progressive merges actually have many spikes downwards. And these are due to the way we create our query selectivity. Since it is generated as 1% of the final data size, there is actually no guarantee that queries have the same selectivity. So these downward points are basically queries that have a much higher selectivity. In the paper, many more points in this presentation are explaining more details. As I quickly showed one of the experiments in the paper, do many more experiments with different data sizes, frequency of updates, and update sizes. You can also find a more detailed explanation of the comparison on robustness and total cost. There's also experiments on appending during the progressive index creation to understand how updates might affect the execution if they start happening from query 1. And a much more detailed explanation of the progressive merge algorithm, going into more depth on query processing and when to merge pieces. So there is still a lot of future work to be done in this area, and I'll quickly talk about the ones involved, but you can find a discussion of all these points in the paper. One major drawback of our comparison with the related work is that they are not really happening with progressive indexing, but actually with adaptive indexing. So to give us an even better understanding of what's going on, we should integrate those to the progressive indexing. In this work, we only explore progressive quicksort as a refined method of progressive merges, but many other algorithms have been introduced in the original progressive indexing paper and can be used to speed up refinement depending on workload and distribution. In this work, we always merge the chunks when they reach a certain size threshold. However, we can explore different merge strategies. Should we keep many smaller chunks or frequently merging them in order to maintain only a small number of big chunks would be better? That's it. Thanks for listening to the talk, and I'm happy to take any questions. Also, feel free to email me or DM me on Twitter if you prefer to chat at any other moments. Thank you.